All right, so in finite element, you just finished the project not very long ago, so I hope you still remember that. So in finite volume, how do you represent the function?
Some basis over, like we have sort of the same volume scheme, so now we have a complex, we have a basis set.
Right, we have the same partition of the space into elements, just different names. You call it volumes in finite volume, you call it elements in finite element, but they are basically partition of the space. And then you represent the function as, for example, a piecewise linear, piecewise quadratic, or piecewise something function in this partition of unity. So if you have piecewise linear functions, and if you have to be continuous, you approximate your function using the function, the closest function that lives in that space. All right, and closest in some sense. And then we are going to be representing that function as a linear combination of basis functions. So the basis functions are functions that are, first of all, satisfies the boundary conditions, and then, let's say this is 1, then they are goes from here to here. They are non-zero in as few elements as possible, right? So this is the kind of basis function for piecewise linear elements. If you want to go fancier and look at piecewise quadratic elements, then I have additional basis functions that are like these. These are parabolas that are actually zero at all grid points, but they just bulge out within a single element and basically enriches the space over that element. All right, so basically you have all these elements, and what do? For each element, you assemble a local matrix, right? For each element, in this case, for Poisson's equation, if you have piecewise linear basis functions, you assemble a 2 by 2 element matrix. That's because in each element there are only 2 basis functions that are non-zero. Okay, if you have piecewise quadratic, what is your size of your element matrix? It's going to be 3 by 3, right? Because you have this additional green basis function. And then what you do, you stack them, right? You look at what are the indices, right, that are shared between different elements, then you stack them accordingly. So for piecewise linear basis functions, every index except for the boundary element gets stacked with something else. But for piecewise quadratic basis function, because the green basis function are per element, so they are actually not stacked with anything else. Only the first and the last element are stacked with the corresponding index from a different element, right? So again, what you get is a sparse matrix, no matter what kind of element you use. So basically, in this case, I get so let's take the quadratic case. You get a 3 by 3 element in the first element. You get a 3 by 3 matrix in the first element. Then you stack it with another 3 by 3 in the second element, and then you stack it over another 3 by 3 in the third element, etc. So you get a matrix that is in the piecewise quadratic case, you get a matrix that is not exactly tridiagonal. You get it a pentadiagonal matrix, right? But still, it's very sparse because the most number of non-zeros for each row is what? 5, right? Okay, it basically corresponds to, if you take any basis function, how many other basis functions does overlap with. So for this one, any of these green quadratic basis functions only overlap with two other elements, right? The linear one on the left or the linear one on the right. Each linear basis function, though, overlaps with four other basis functions. You have a linear one on the left, a quadratic one on the left, you have a linear one on the right, you have a quadratic one on the right. So that's why we have a slightly denser matrix. So the number of non-zero entries in the finite element corresponds to the overlapping, like what is the called the support of a basis function, like how wide it is and how many other basis functions are active within its support. All right. So basically you get a sparse system also to solve. So this is why solving sparse systems are so important in PDEs. And if you look at the area, like in linear algebra, of all kinds of methods for solving sparse linear systems, they all pretty much grew out of the PDE community. So those who work on PDEs was promoted by the necessity of solving large sparse linear systems and developed all kinds of methods to deal with them. Okay.